Hello everybody, welcome back. In this video, this is another one pulled from my actual Zoom lecture and class. In this video, we're going to talk about the extreme value theorem and the intermediate value theorem. This will almost finish off our lectures on continuous functions and compact sets. We'll have one more that will talk about something called the intermediate value property. So I hope you enjoy it. We'll do the extreme value theorem first, because it's actually, the proof is going to be quite short now. So we're going to start with a continuous function, and we're going to assume that D is compact. Okay, so the claim is that if we look at all of the elements of D and we evaluate F over all of those, then there is going to be a minimum value and a maximum value. So before we prove this, let's see what can go wrong. So this is a non-example. So let's say I look at f of x is equal to x squared. And I let my domain be the open interval 2 to 5. So I look at all of the possible outputs, right? The image of f on D. So what is the f image of D here? The open set from 4 to 25, right? So this is an increasing function. You don't get 2 squared because 2 is not in the set. You don't get 5 squared at the end because it's not in the set, but you get all the stuff in between, right? 4 to 25. What is the maximum value in this interval, 4 to 25? What is the largest value? A value in here that that's in the set, but nothing can be bigger than it. It's like, let's say I thought this was my max value, X. And I say, well, X definitely is less than 25, right? But we have this density property, right? Density tells us if I have 2 real numbers, I can actually find a real number in between them. And this y would also be in the interval, and it's bigger than x. So x can't be the maximum. So y is the maximum. No, because then you just do it again. You say, well, there's something in between y and 25 by the density of the reals again. So actually, there is no maximum. Does not exist. And for similar reasons, right, the min value in 425 does not exist. Now, what does exist? If I'm trying to talk about the max value in this set, and we say, well, that doesn't exist, but like if you were talking to a kid and they don't know what open intervals are, right? You just say, okay, all the numbers between 4 and 25, and you say, what's the max value? What is a kid gonna say? 25. And now you being, the good adult with a strong mathematical background, you say, well, I'm sorry, idiot. I mean, kid. I'm sorry. No, there is no max value in there because density of the reals and all that. But that 25 is the what of the set, the infimum. Okay, so this is a fun way to be condescending to the children. You silly little child. You don't know the difference between a maximum and a supremum. Okay, very important when you're in mathematics to be elitist. It's the most important lesson of the day. Okay, so the maximum and the supremum are different. because the maximum has to actually be in the set you're talking about. Whereas the supremum doesn't, right? It's just some least upper bound, right? The infimum, just some greatest lower bound. Doesn't actually have to be in your set. Okay. Now, in the special case where the supremum is in your set, then the supremum is actually equal to the maximum, yeah? The maximum is supposed to be the largest thing in the set. Well, if the supremum is bigger than everything in the set and it's in the set, then it must be the maximum. Okay. And this is what compactness is actually going to give us. Compactness is going to always put the supremum and the infimum into the set. And hence the maximum and the minimum are going to exist because they're the supremum and the infimum. All right, so let's try to prove this. It shouldn't be super long. Now, there's two statements here, right? The min and a max both existing. I'm just going to do the min for a change, right? Everybody else would do the max, I think. So let's see. What do we know about f of d? F is a continuous function. D is compact. So what can we say about f of d? It's compact. Why? Because exactly, right? Continuous images of compact sets are compact. Okay, so we know that f of d is compact. Fine. Okay, but f of d is compact means that f of d is closed. Bounded. Yeah. Okay. Fine. Well, I guess, probably we should be saying something like this set is non-empty to begin with, right? So let's just assume D is non-empty. Otherwise, this statement doesn't make a whole lot of sense. Okay, so it's closed and it's bounded. Well, if it's bounded, and remember, we're looking for a minimum, but what do you know about a non-empty bounded set? It has a what? Infimum. Okay, cool. So by the axiom of completeness, the infimum of f of d exists. But the closure tells you then that the infimum is in the set. Yeah. So this tells you the closure combined with that it exists. The infimum is an element of f of d. So we start with a compact set. We apply f to it. We get another compact set, which means that that set is bounded, which means it has an infimum, but also the set is closed, which means that the infimum is in the set. But if the infimum is in the set, and it's the smallest element in the set, right? Because it's smaller than everything in the set, and it's inside the set, it must be the minimum. So this implies that the infimum of f of d is equal to the minimum over all elements in D of f of x. And that's it. That's the whole proof, right? Similar for max. Right? You just use the supremum argument. And then we'll this is the second of our value theorems. Before I write down the intermediate value theorem, I want to prove one sort of lemma, but I'll also just call it a theorem. It's usually proved or just said as the part of the proof, but I think it's useful. I didn't come up with this name, but I kind of like it. So a guy named Stephen Walk. He's not the first one who noticed this or proved it. He just gave it the name, right? So this is named by. Stephen Walk. He calls this the aura theorem. So you don't know what an aura is, right? So some people believe that we give off some sort of energy that manifests itself maybe in some sort of a light or something floating around our body, and some people claim to be able to see this light emanating from our bodies, and they call it an aura. And so let me draw a picture so you can see why this is maybe called the aura theorem. So we're going to have some function f, and in this case we're just going to take some open interval a to b. Okay, I'll just write that down. Let f go from a, b to the real numbers. Okay, there's our real number line. Be continuous. Okay, so we have a continuous function, and then I choose some point in between a and b. Okay, so let s be in between a and b. All right, I apply f to s, and I get f of s. All right, now there are three cases. F of s could be 0, and in the aura theorem, we don't care about that case. We're just tossing it out. The other two cases are that f of s is positive or that f of s is negative. So in this picture, let's consider the case where it's positive. Okay. So if f of s is positive, of course, there's another picture where it's negative. Okay, then, well, what should happen? Because f of s is greater than 0, I can find some coin for f of s that is small enough that I don't get down to 0. Okay, so I get a coin f of s where the entire coin is positive. Okay, fine. But now f is a continuous function. And what did it mean to be continuous? It meant that, okay, when I have this coin around f of s, then I can find some coin around s that is going to completely map into this f of s coin. Okay? And because this f of s coin was all positive, then, well, I know that the image of everything near s, right, in this coin is going to be positive. Okay, so that's the statement here. So then there exists an s coin whose f image is positive. Of course, if we were in the case where f of s was below 0, then this f image would be negative. Okay, and that's all it is. Okay, is you're basically, once I know this point f of s, right, and I have this point s, I know I can put this little halo around s, where not only does s go to something positive, but all the stuff in the halo goes to something positive. Okay, so that's where the name of the theorem comes from. Okay, and the proof is just continuity. Okay, so proof follows from the continuity of f. All right, see the thing I explained, right? We know for every f of s coin, there is some s coin which is going to map into this f of s coin, but this f of s coin is positive. Okay, so that's that. All right, so we want to use this aura coin in the proof of the intermediate value theorem. So that's why I have it first. So our second value theorem, intermediate value theorem. All right, so what is the intermediate value theorem saying? So it's going to say you have some function f, which is continuous, on some compact interval AB, right? It's really going to be a closed interval here. So f is going to go from AB to the real numbers, and it's going to be continuous. And we're going to assume that when I apply f to A, I get, well, of course I get f of a, that this is going to be less than f of b. There's, of course, a similar statement where f of b is less than f of a. Okay, so such that f of a is less than f of b. All right, and now I choose some point in between f of a and f of b on the y-axis. Okay, so let f of a be less than c, be less than f of b. Okay, well, I mean, I'll say if this is true. So if c is between f of a and f of b, then the claim is, let's draw this little dashed line here. The claim is that there is some point in between a and b such that when I evaluate z with f, I get c. So c should be f of z. Okay, and the point is this is assuming f is continuous. There's no way that I can connect these two dots together without crossing that line. Right? I can't skip over any point on this between f of a and f of b. So the statement is then there exists some z between a and b such that f of z is equal to c. Okay. So how do we prove this? Well, we're going to do a little transformation first to make our life slightly easier. What I want to do is to slide everything down by c. All right, so everything's going to go down by c. So this would be f of a minus c. And c, if it goes down by c, would go to 0. And then f of b goes down here, and it's, like f of b minus c. Okay, so the way I'm going to do that formally is I'm going to let g be a function where g of x is f of x minus c. Okay, so just everything, like this whole graph, right? Everything is moving down, right? So, f of a is down here now, except it's now f of a minus c. Then we have there's our f of b minus c. F of b minus c, right? And of course, this c is supposed to come down here, actually, to height 0. Okay, so I just want to show now that I can find some point z such that the actual value of g is 0. Okay, so again, making this rigorous a little bit. So if I take g of a, this is equal to f of a minus c. And since f of a is less than c, then I know that f of a minus c is less than c minus c, which is 0. And since c is less than f of b, then if I subtract c, I'll be less than f of b minus c, which is g of b. Okay. And because I'm taking the difference here of two continuous functions, then by the algebraic continuity theorem, g is continuous. Okay, so I now have a continuous function, still on AB. G of A is less than G of B. I have some point C in the middle, which is now but just 0. So I have 0 between G of A and G of B. And I want to show, so we want some Z between A and B such that G of Z is equal to 0. Okay, so this just makes our life marginally better. Okay, so should be able to get this argument out. So what do? We're going to make a set, and here's the set. I take all the points between A and B, but I only look at the ones where the G of those points is non-positive. So I'm looking at all points X between A and B, such that G of X is less than or equal to 0. Okay, now I know that G of A is negative. Right? I said that up here. So that means that A is in this set. Okay, so this contains A, which means that this is non-empty. Also, B is the largest possible value that could be in this set. So this is bounded by B. So I have a non-empty bounded set. And so by the axiom of completeness, I know that the supremum exists. And this is what my Z, that's the Z I'm looking for, is going to be. Okay, so I'm going to set Z equal to that. Now, of course, I need to show that this works, right? Well, of course, if G of Z equals 0, we're done. So let's assume it's not 0. If it's not 0, then G of Z is either positive or negative, and both cases are going to be mostly similar. So let's just handle one of those cases. So we'll assume G of Z is positive. But now we get to go back up to the aura theorem. If the image of our function is positive, then we can find some coin around the input whose image is still positive. Okay, so in this case, if G of Z is positive, then by the aura theorem, there exists a Z coin whose G image is positive. So we have a Z coin whose G image is positive. But I claim that's impossible, right? That this is a contradiction already. Because what was Z supposed to be? Z is supposed to be the supremum of this set. What is this set? It's the set of all numbers between A and B whose image is not positive. Okay, but now you take some Z coin. There's Z, here's Z minus delta, here's some Z plus delta. And you have all these points in the middle here where G of whatever is positive. So how can Z be the supremum, right? Z is supposed to be the biggest. So that means you know that all of these points are to the left, but here are smaller points, which are also upper bounds, right? Every one of these is an upper bound for this set, right? Which must be over here somewhere. But Z is supposed to be the least of the upper bounds, but we found smaller upper bounds. So this contradicts Z being the supremum. Okay, so we make a similar argument when G of Z is less than 0, right? When G of Z is less than 0, again, we'll get by the aura theorem a Z coin whose G image is negative. But then you can look at the top half of this stuff, right? So if you're looking at stuff where G of Z is now negative, well, all these things are bigger than Z. And they're in this set, right? They're in this set that Z is supposed to be the largest stuff, right? It's supposed to be the supremum of it, but we have bigger things in there. Again, this would be a contradiction. Okay, so this contradiction comes from either us letting G of Z be positive or G of Z be negative. So we conclude that G of Z is 0, and that ends the proof.